All right. Next thing I want to talk about is the sigma level index and why it's called 6 sigma. It's always interesting to me is that we have this thing, we were taking a class on 6 sigma, and many of us don't really understand where it comes from, and it's hard to explain until we get a certain amount of material. So we have to get a certain amount of material in the class before we can effectively explain where the index comes from of the 6 sigma level. What's actually kind of interesting is that although we call this 6 sigma or lean 6 sigma, and people talk about the sigma level index as the metric, over time, many people have stopped using the sigma level index as a metric, and I'll explain why, and they still use all the tools and methods. So there is not necessarily a widespread adoption of converting everything into what's known as the sigma level index. But this term, sigma level index, that comes from Harry, thought of as the founder of the DMAIC and this process. And what he did was he said, you know what, I need to have a new scale. And I want to take basically yield percentages and put it on a different scale. And I'm going to call this the sigma level index scale. And he did this, and he even incorporated what he called the mean drift into the index in order to come through this. And in order to understand this process, it takes a few slides to kind of understand what he really did and why he did it. All right, we begin with the case where I could look at data, and I could have a situation where I have a process which has extremely high capability. And earlier in the class, when we talked about process capability, I suggested to you that a CP of 2 is really good. A CP of 2 means I could fit 2 distributions inside my specification. Or you could take 1 over 2, and you could say that my 6 sigma distribution is only 50% of my tolerance range. Right? And what Harry said was, you know what? We need to drive to very low variation. And our goal should be a CP of 2. And if you have a CP of 2, what you end up with is plus or minus 6 standard deviations equal to the tolerance. See if you can follow along with that, right? CP is USL minus LSL over 6 sigma. And if it's a 2, that means that the USL minus LSL would be equivalent to plus or minus 6 or 12 sigma. Everybody see that in terms of a number? And he said if you have a centered process with a CP of 2, you're going to get virtually no defects, 0.002 per million. The tail is extending out. And then what he said was, one reason why this is important is that if you look at historical data of most processes, the mean is not at nominal. Most processes, if you pull the historical records, and this is a reasonable statement, by the way, the mean is often drifting, right? If you do an X bar chart, a lot of times your X double bar is not the same as the nominal value. There is a drift in the process. And he said, you know what? We need to allow this drift to happen. We need to allow this drift to happen. And then he put some numbers on how much drift to allow. And he said, you know what? If we allow this drift to happen, and we are able to still have a gap of 4.5 sigmas between my mean and my upper spec limit. If you make a z value of that, z is the USL minus the mean over sigma, you'll get a z value of 4.5. And if your z value is 4.5 and you go to a normal probability table, that equates to a 3.4 per million. If you go back in class, I gave you a normal probability table. Look up a z-score of 4.5. Z-score of 4.5 is equivalent of 3.4 per million. And what he is saying, which is really quite logical, is that my mean is going to drift. And if I can get a CP of 2 I can allow my mean drift to be all the way up to 1.5 sigma, and I'll still have a good enough control where I'll only get 3.4 million. Therefore, we're taking this distance of 6 sigma, and we're allocating it to 1.5 to allow for the mean drift, and then the tail of that distribution to only have the 3.4. And he did this because he said the people in industry were making the mistake of always assuming mean equal to target or mean equal to nominal, and that they had to have even higher quality in order to have very few defects. Now, when the mean shifts 1.5 sigma to either direction, what happens to the likelihood of a defect on the other side? It's very small, right? Go look up a z-score of minus 7.5. It's a very small number, right? So you have a very low probability. How did he come up with 1.5 sigma? No one really knows. No one really knows. Mystery. I have my own theory of that, but he basically said, my experience says, right? And people said, all right, sounds good, right? Most of us know that there is a drift. What that exact drift is going to vary by industry and product and all kinds of things. We've got to be a little careful with knowing that. But it's reasonable to say that things drift. And it's been pointed out by other people. There's actually a person named Bender who suggested this before McElharry, but he doesn't get credit for anything, so who knows. Anyways, this idea of a drift is going to happen. Now, McElharry, if he would have stopped there, he probably would have been great. But he went and he turned this same concept into an index. In order to do that, we have the following formula. We're going to go out and we're going to take the yield number. And so if the yield number is 99.99966%, which is the 3.4, and I do a norms inverse of that, norms inverse of 0.9999666 is 4.5. And then I'm going to add 1.5. And if that's the case, you get a new score of 6 on the sigma level index. If your z value was, or your yield was 0.9, you would look up the z value associated with 0.9, and you would add 1.5. All what he's doing is he's converting yields into a new scale. He's still using specifications. He's just converting it to a new scale. How do I get that yield? Well, that's going to depend on what kind of data do I have. If I have a case of normal, I could get 1 minus the probability of a defect. If my data was Poisson, I could take e to the minus defects per unit. If my data was binomial, I could take 1 minus the fraction defective. All of those could be converted to a yield, and then they could be converted to an index score. As a simple example, if the yield was that's a z of 4.5 plus 1.5, you get a 6. If your yield was 83.54, take the norms inverse of that, add 1.5, you get a 2.48. Then what McElharry said was typical industry is 66,000 parts per million, which is a sigma level of 3, and we want to go higher. And you can see as you increment that, if you were at 230 per million, you'd be at an index of 5, and you have to get all the way down to 3.4 per million to get to his number 6. By the way, what if you had a... I won't go there. All right. You get the 1.5 no matter what. You just get it. Well, so I was going to go there, but since you brought it up. What happens if the yield is 0? I do it this way. What happens if the yield is 50%? 50% defective. What's the Z value for 50%? Somebody? Z value for 50% defective? 0, right? So even if you had 50%, you'd have that. If you fall below that, you'll get negative. You can get a negative on the sigma level index. You can get a negative value. I'll let you do that on your own if you want to, or trust me. You can get a negative value for the index. All right. I've given you a little template. If you want to play around with these, you could plug in any number of the yield, and the software will come back and give it to you. If you want to play around with that. Arguably, you get to negative infinity. It's tricky. All right. Are we okay? Plug and chug if you were curious. Not a test question. Please, no test questions then. All right. I want to bring another last point to this and tie this to our process capability indices, because they're related. If we come back and we think about our CPK index, if this is our USL and that's our target and we're shifted such that the gap here is 4.5 sigma. All I'm doing is poorly redrawing that picture. All right. If that gap is 4.5 sigma, and I do a CPK, CPK is USL minus the mean, that's 4.5 sigma, divided by 3 sigma. 4.5 sigma divided by 3 sigma would be 1.5. A CPK of 1.5 equates to the 3.4 per million. CPK of 1.5 is 3.4 per million. A CP of 2, right? And if I took that CP of 2, right, and then I let the mean drift to a 1.5, I'll be at 3.4. I'm going to say this again. If I told you that you have a CP of 2 and a CPK of 1.5, your sigma level index score is equal to 6, and your parts per million is equal to the 3.4. Kind of follow me on that a little bit? Essentially, you have a CPK requirement of 1.5. Prior to Mikkel-Harry, many people in industry, particularly the automotive industry, had a requirement of a CPK of 1.67, which is like 1 per million. It's fascinating to me that Mikkel-Harry was able to convince people who had a 1 per million criteria that their quality standards weren't high enough and they should move to the sigma level index goal of 6, which is technically a lower standard they were using before that. But they didn't understand enough about statistics to know that was going on. So they were convinced that he was offering them a higher standard when technically he was offering them 2 less than their current goals were. Kind of funny if you step back and think about it, right? People like me chuckled. Most people were like, what? I don't get it. Okay. So anyways, my point here is we make standards. And when someone says our standard is a CPK of 1.67, that's a very high standard. It's actually technically higher than a sigma level index score of 6. 3.4 versus 1, basically very similar to that. But what they're doing here is very much related, right? What Mikkel-Harry is doing here is very much related to this notion of CP and CPK. Get your CP high enough so that your mean can move around in order to have a very low parts per million defective. The concept is very sound that way. All right, to wrap things up, right, you can use the index score to quantify your performance. On the positive side, it reinforces this idea that you're going to have some mean drift, right? On the negative side, the assumptions of always adding 1.5, not really all that great. The assumption of adding 1.5 if the data was binomial is not all that great. All right? So there are some general concerns with that, and as a result of that, there are some people that just use yield, parts per million, defects per million opportunity, and do not anymore convert it to this sigma level index. Sometimes you may work for someone that still uses the sigma level index. Conceptually, it's good because of the idea of a drift. The math behind it is ish, but that's okay. Right? Any questions before we wrap up? All right, awesome. We'll see you next time.